I haven't seen yet my first uploaded YouTube video with the black pen, so I'm curious to see whether you're finding, or I find, that there's more contrast with a black pen than a blue. Anyway, we'll see. Alright, well, continuing on with the quantum mechanical analysis of the simple harmonic oscillator. Previous session we found that the energies were quantized, the allowed energies. That's sort of not surprising for quantum mechanics or quantized mechanics, right? And for the SHO, the energy values were n plus a half times h bar omega. They're the allowed energies, right? Now you can just see the difference in energy value between, say, E5 and E6 is just 1 times h bar omega. So the allowed energies are equally spaced, right? And you can see that just obviously from here. Now the lowest possible energy is when n is 0, so E0. We usually call that the ground state, the lowest ground level state, if you like, energy, and it's obviously just a half of h bar omega, right? Alright, so what then is the wave function? Well, U0 was proportional to this value, so make it a constant and then normalize the thing to get so you know what this constant is. Do that for homework. Here's the normalized, the actual value for the wave function at the ground state, 0. When n is 0 here, you get this. So this constant here is quite involved. It takes a bit of work. Okay, so now that we know the eigenvalues, in other words the energy for the simple harmonic oscillator, the SHO, the show, and we know the eigenstate, in other words the wave function, for the ground state energy, for the ground state, it's this, right? So now we can start using this. If we square it, we get a probability density, and if we have the probability density, we can calculate average values of various things. For example, well, say you've got a quantum, something's oscillating, some quantum system's oscillating like this, say between amplitudes, U minus A or whatever. Common sense, what do you think the expectation value, in other words the average value of its position would be? In other words, the average value of x, which is what's being asked, here. Now, remember from earlier lectures, if you see this angular bracket in quantum mechanics, in the context of quantum mechanics, it has completely different meaning in, say, group theory, but never mind. But in quantum mechanics, this angular bracket is asking you to find the average value of whatever's inside the brackets. So what you're being asked to find here is, what is the average value of x? Well, you'd expect it to be 0, wouldn't you? I mean, it's spending as much time on the right hand side as the left hand side, so you'd expect the average value to be 0. And that turns out to be the case because, well, why? Well, have a look at U0. Here it is here. If you look at this is an even function, right? It's a function of x, so f of minus x, well, you put a minus x here, but it's squared, so it makes no difference. So this is an even function. So U0 squared is an even function times x. Well, x is obviously an odd function. Minus x is just minus x. So the product of an even function times an odd function gives you an odd function. And if you differentiate that over plus or minus the same limits, you get 0. So that confirms, that mathematically confirms your common sense feeling that it should be 0, because it's as much, the particle's as much on the left hand side as the right. Now, what about the average potential energy? Because your V depends on your V is half kx squared, right? So this would be a lot less trivial. Well, to find to find the average of anything, you integrate whatever it is, anything. You integrate the anything by the probability distribution over whatever range that you have. So so the average of v, well, here's half k x squared. That's your v. That's the thing you're trying to average, and your probability distribution is just u naught squared. Oh, we're talking about the ground state, right? The average value of the potential energy for the ground state. Well, you probably have to non-trivial. You plug this in here, so you've got e to the minus k x squared times x squared, and you're integrating that. You probably need a let's see. There's an appendix here with useful integrals. Let's see if it has that particular problem. E to the minus. If I can find it quickly, not waste too much time. Useful integrals. E to the minus x squared times x squared, I guess something like that. Yes, yeah, there is something, sort of. Okay, so you can look up a useful table of integrals in the text, help you solve this problem. So u squared, so you'll have e to the minus x squared, the 2 will disappear, and so forth, and you end up just getting a half of E naught, right? So E naught, V naught. So it's just a half of E naught. So it's what would that be? A quarter of h bar omega, right? Now, what about the expectation value of the kinetic energy? Well, the total energy is kinetic energy plus potential energy. So you'd expect the average kinetic energy, or expectation value of the kinetic energy to be the difference between the average total energy, and that's just a constant, right? It's here, it's given, E naught, it's just a half h bar omega, minus the average potential energy, which is a half E. So if that's E minus a half E, you just get a half E. So that's saying that the average potential energy is equal to the average kinetic energy, which is sort of, it seems to make sense in an oscillator. At its maximum extension, it's not moving, right? But the potential energy is sort of maximum, and then pulls it back and it speeds it up, so the kinetic energy is increasing until it's at the middle point, and there the spring is neither stretched nor squashed. So its potential energy then is nothing, but at maximum kinetic energy. And energy is conserved, so it's converting potential into kinetic and kinetic into potential the whole time. So it's not surprising these two are equal. Okay, so the average kinetic energy is equal to the average potential energy, and that's just the same as in classical mechanics. So it's not surprising. That's also true for quantum. Okay? And this phenomenon, now all this analysis here is for the ground state energy, but it happens to be true also for higher levels, when n is more than 0. Okay. Alright, so we've found the ground state energy. Now how about higher states, higher energies, when n here is greater than 0? How do you go about doing that? Not so easy. You remember our Ansatz, A-N-S-A-T-Z, our trial function, and we said it took the form of some polynomial f, capital F of z times this form here. Okay. Well, then we have to put in the full polynomial, all of it in this equation. That was our equation for the simple harmonic oscillator quantum case. This second order differential equation, d squared f dz squared minus 2z df dz plus f times 2 epsilon minus 1 here. This. Okay. And we'll come back to this equation because it's a special equation, and so I've got a bit star here to ID it, to identify it, because I'll come back to it a bit later. All right, now so you put in your polynomial z to the n plus a z to the n minus 1 plus b z to the n minus 2 dot dot dot. Okay, and you put that f, your polynomial, into this equation, and then so the left hand side is equal to 0. So all those coefficients of z to the n minus 1, z to the n minus 2, all those coefficients have to be equal to 0, right? So for each power of the coefficient for each power of z has to, those coefficients have to be 0. Right? That's what's been saying here. Okay, now actually do that. So plug in try an f that's of the form z, so power 1, z plus a constant, and you can calculate what the constant would have to be for satisfying this formula, and you find that it's 2, right? And if the power of z is nothing, so just 1, then your f is in fact just 1. If